Hello, our names are Matthew Haldeman,
Elizabeth Hance,
Ben Jones,
Sara Brumbaugh,
and Kevin McDaniel.
and we're mathematics majors from Marshall University, working with the Huntington Police Department on a project for the PIC Math program, which is sponsored by the MAA, NSF, and SIAM. The Huntington Police Department has not redrawn their patrol zone map in nearly 15 years, and it has become obsolete. The current map is shown here on this slide. They currently use 6 zones with 1 officer assigned to each zone and 2 cover cars, an east cover car and a west cover car that can roam freely between zones. The data shown here tells you why this plan is obsolete. Some of the zones, such as Zone 2, have about twice the geographical area of other zones, such as Zone 6, while some of the zones, such as 1 and 2, have twice the number of call volume as the other zones. We've considered 3 major guidelines in deciding how to redo these patrol maps. First, we are considering anywhere between 6 and 10 cars patrolling the city, with 1 car assigned to each of the zones. Additionally, these zones can vary based on the shift, so perhaps in one of the shifts you will have more cars than in the other shifts to better cover a higher concentration of calls. Additionally, we have considered both having cover cars and eliminating them, and as we will explain later, we chose to eliminate them in all of the plans that we will be presenting. Also, in Huntington, we have a railroad track that runs through the middle of the city and viaducts that go underneath it so that cars can pass underneath the railroad tracks. Huntington is also very prone to flooding, and in the case that there's a bad flood, these viaducts will flood very quickly, cutting off some of the zones, such as zones 2 and 3, which span the viaduct. So in this case, we have decided to try to have viaducts on the outsides of zones so that they do not cut the zones off.
We began by analyzing some of the data that we were given. We found that zones 2, 3, and 4 contributed to over 60% of the call volume, whereas it should be a more equal distribution. We also found that the call volume tends to increase in the spring, specifically April to July. Finally, we found that there was a slight increase of calls from Thursday to Saturday, but this was less than 1%, so this may indicate that it's not necessary to change the number of officers throughout the week as we had previously anticipated. We analyzed the amount of calls throughout the day. The graph here shows an increase of calls at 3 p.m. and a decrease of calls around 5 a.m. Currently, a shift change occurs at 3 p.m. Because of this, we decided to propose an alternate shift. Currently, the shift change occurs at 3 p.m. However, this is when the most calls occur throughout the day. As a result, we proposed an alternate shift in which the shift change would occur at 2 p.m. Additionally, with this alternate shift, the day and midnight shifts have a more equal distribution of calls.
The Naïve maps were the first attempt at drawing maps for the Huntington Police Department. The maps were created using human intuition and were later optimized using the method of gradient descent. The maps were created with anywhere from 6 to 10 zones, with 1 officer per zone. These maps can also be implemented using anywhere from 0 to 2 cover cars, depending on the budget of the department and the number of zones. The factors we considered when drawing these Naïve maps were the viaducts, crime distribution, and area. For the viaducts, we want them to lie on the boundaries so that a viaduct does not split a zone. In terms of the crime distribution and area, for zones that have a higher crime rate, we want the area to be smaller, and if the crime is lower, then the area will be larger. Here you can see an example of a 9-zone Naïve map. The dots on this map represent the viaducts within the city. As you can see, the viaducts lie only on the boundaries of each zone, and there are no viaducts that split the zones. Also, the zones that have a larger area have lower crime rates, and the zones with a lower area have a higher crime rate. This chart shows the daily percentage of calls per zone per shift. As you can see, the day shift and the midnight shift have around the same amount of calls, with 5 to 6% of the calls per zone per shift. The evening shift has more percentage of calls, between 8 and 9% per zone per shift. This indicates that we may consider day shift and midnight shift having the same number of zones on each plan, and the evening shift having more zones. This chart shows the daily percentage of calls per zone per shift in the proposed change. These results are consistent with the last slide, so we would still want to consider having more zones in the evening shift than in the day shift and midnight shift.
In addition to using human intuition to design new zone maps, we also developed a numerical method for evaluating the fitness of a map. We call this the fitness function. It involves a series of mathematical models that each measure the goodness of a plan with respect to some topic and combines their outputs into a score that allows plans to be directly compared. We considered a number of topics and decided to model local and global response time, workload distribution, patrol time, and viaduct avoidance. We chose to construct these models so that lower scores correspond to better plans. For local response time, we employed a method based on similar research done for Charlottesville, Virginia, which incorporates the probability of crime occurring at a location and the distance from a zone's centroid to that location. Global response time measures how quickly all the patrols can converge on a high-priority call. Its computation is similar to local response time, but instead involves a set of hotspots that were identified as likely locations of violent crime. The workload distribution model computes the standard deviation of the call frequencies of the zones. A good score in this term means the call distribution is well balanced, so every zone has around the same workload. Patrol times were approximated by averaging the ratios of each zone's perimeter to its area. A bad score in this term means some of the zones are stretched out, and a good score means all the zones are nice and blobby. Viaduct avoidance is scored as 1 plus the proportion of viaducts that are not on the border of the zone. We combine these scores together using a weighted geometric mean, which allows us to preserve both the direction and relative magnitude of the scores without having to know the model's output ranges. The weights are computed as a product of relative weights, which were provided by our liaison with the police department based on his intuition, and adjustment weights that were chosen to normalize the average magnitude of change we observed in each model.
We have these naive plans, and we also have a method for evaluating them, but we would like to see if they can be improved in even a small way. So we've done that through a method of gradient descent. It works basically by pixelating the city, and then for those pixels that are on the boundary of a zone, moving them to the neighboring zone, and then taking the change that improves the score of the fitness function the most. This algorithm can continue for a set number of iterations or until a locally optimal plan has been reached. This is an example of a 10-zone plan that has been pixelated. Here it is after 60 iterations through the optimization function, again after 120 iterations, and finally at 180 iterations. None of these changes have messed with the overall layout of the map. Instead, they're meant to find a local extremum for the function. One of the problems with this method is that it doesn't respect roads or railroads. So some of the boundaries can be rather strange, and they must be smoothed over for a workable result, which we have here, the smoothed over 10-zone map.
The fitness function assigns a score to each of the different potential plans and basically gives us a system of ranking them relative to one another. However, we've also developed a discrete event simulation that allows us to accurately simulate the entire dynamics of police patrols responding to crime in the city. The outputs are physical parameters, such as response time and number of calls per car. So we import the entire map of Huntington as a graph, where the nodes represent intersections and the edges represent roads, and we can use pathfinding algorithms to control the movement and timing of cars around the city. We program in virtual patrol cars that are programmed to understand how to respond to the calls that come in, and we import historical crime data from the Huntington Police Department so that we can run the entire simulation through real-life crime data. This slide shows some of the data that we've extracted from the discrete event simulation. For each of the different zone plans on the left, we can calculate the time it takes for the first and second cars in the simulation to arrive at the call. Additionally, each car keeps track of how many calls it responds to during the entire week of data, and we can keep track of the workload deviation and coefficient of variation between each of these cars. Ideally, we want the response time to be low and the workload deviation to also be low. In this data, you can see that as you add zones to a particular plan, the response time decreases in each case. Here, there's no clear trend in the workload deviation as a function of the number of cars. Based on our analysis, we have decided to propose the 7-10-7 scheme as an optimal plan. That is, during the day and midnight shifts between the hours of 6 a.m. and 2 p.m. and 10 p.m. to 6 a.m., the city would be divided up into 7 zones with 1 car per zone. However, during the more busy evening shift between 2 p.m. and 10 p.m., the city would instead be divided into 10 zones with an officer in each zone to cover the higher concentration of calls. As you can see in the total row at the bottom of this chart, the highest number of calls do occur during the evening shift, 44%. However, if you look at the average percentage of daily calls in each zone for these shifts, in this scheme, they are nearly equalized, with each equaling about 4%. To sum up the conclusions that we've made in this project, we discovered that the naive maps created using human intuition actually worked quite well. In this case, they changed very little under our optimization routine, and oftentimes, after optimization, scored worse in the discrete event simulation. However, the weights of the optimization routine can be tweaked, and we plan to revisit these in order to see what other results we can get out of it. We discovered a clear correlation between the number of zones and the response time. As you add zones to a plan, the response time decreases. We have proposed a shift in patrol times, moving each of the shift changes back an hour, from 7 to 6 a.m., from 3 to 2 p.m., and so on. Additionally, we have proposed the 7-10-7 scheme as an optimal plan for the City of Huntington. We have recently presented our findings to HPD, and they are currently weighing their options to decide how they want to use our information. We would like to thank the PIC Math program in conjunction with the NSF, MAA, and SIAM for their support in this project. We would like to extend our thanks to Dr. Michael Schroeder, our faculty advisor, and to Mr. Scott Lemley of the Huntington Police Department, who supplied us with this problem and all of the data and insight that made our solution possible. Thank you.